Hi everyone. In this video we will continue talking about the one sample t-test. In our previous class on Monday we talked about the one sample t-test, what it is, what it allows us to test, and we walked through several examples of how to do the test by hand. In this video we will quickly review what the test is all about, and then we will look at how to perform this same test in SPSS, and in so doing we will compare the process of doing it by hand versus doing it in SPSS. Before we go any further, I just want to remind you that the content of this video will not be on next week's midterm exam. You will need to know how to do this test by hand for the midterm, but you do not need to know how to do it in SPSS for the midterm. However, you will need to know how to do it in SPSS for the final exam. Here is a quick review of what the one sample t-test does and the 7 steps that we went through in class on Monday when we wanted to perform it. So remember, in a nutshell, what we're doing with the one sample t-test is we are collecting data from one sample of people. We are calculating the sample mean for those individuals, and then we are testing to see whether that sample mean is or is not significantly different from some benchmark number, which we call mu. So it might be 8 hours of sleep, which is the recommended amount. It might be 1059, which is the average SAT score, or some other number. The point is, we have a sample mean, we have our mu. We want to know, are those numbers different or are they not different? Here are the 7 steps that we did to perform the test. First, as always, we state our null and alternative hypotheses. We then calculated the standard error in step 2 and the t-statistic in step 3. In steps 4 and 5, we found the critical t-values, and then in step 6, we compared the t-value that we calculated in step 3 against the critical t-values that we got from the table in step 5, and we made a decision about whether we were going to reject the null hypothesis, meaning we have found a significant difference, or retain the null hypothesis, meaning we have not found evidence of a difference. And our last and arguably most important step is to write up our results in a complete sentence in proper APA format. Here again is an example of how we did that in our first in-class example from Monday. A one sample t-test showed that psychology majors' GPAs were not different from the college-wide average. A quick review of the important elements of our answer here. First, we always start by naming the test that we used, and we want to make sure that we are explaining the results of our test in a single, complete, grammatically correct, and clear sentence. My advice is to write the sentence first, and then you can go back and insert the numbers where they are appropriate. In blue here, we have our descriptive statistics. So next to where we talk about psychology majors, we report the sample mean and the sample standard deviation from our study. Next to where we talk about the college-wide average, we report the value of mu, which in this case was 3.06. And then at the very end of the sentence, we report the results of our t-test. So we have a italicized t with 8, which is our degrees of freedom, in parentheses. The t-value that we calculated in step 3 was equal to +2. And because we retained the null hypothesis, not rejected it, we say that p was greater than 0.05, which reiterates that we did not find evidence of a difference between psychology majors' GPAs and the average GPA across the whole college. We will now see how to perform this same one sample t-test in SPSS. Our first example pertains to lying in your online dating profile. Surprise, surprise, people sometimes say things in their dating profiles that aren't true. Take a second to think about what sorts of things people might lie about when they're making a dating profile, and whether men and women might lie about different things and what those things might be. One thing that men might arguably lie about is their height. They might exaggerate their height to make themselves seem a little taller than they actually are. We happen to know from the CDC that the average US adult man is 175.9 centimeters tall. In other words, that is our population average height for men in the United States. Now, assuming all sorts of different people use online dating websites, If people on those websites are being truthful about their height, we should find that the average male OkCupid user is 175.9 centimeters tall. However, if men are systematically lying about their height and trying to make it seem like they're taller than they actually are, what we might find is that when we took a sample of OkCupid users, men, and we saw on their profile how tall they say they are, that their average advertised height is actually higher than 175.9 centimeters. That is the hypothesis that we are going to test. So the data file okheight1.sav, available on our website, as are all of the data files that we'll use for the whole semester. This data file contains information from a sample of men who have a dating profile on OkCupid. And for each man, the only piece of information we have is how tall their dating profile says they are. Now, remember, if they are being honest about their height, what we should find is that the average height in our sample is not different from the average height in the general population. So our null hypothesis here would be that the mean height of male OkCupid users in our sample is not different from the population mean of men's heights, which the CDC tells us is 175.9 centimeters. Here is what that data file looks like. So again, we have data for a whole bunch of male OkCupid users, and for each man, we know how tall their profile says they are in centimeters. To run the one sample t-test, we're going to go to Analyze, Compare Means, and select the option for one sample t-test. When we do that, we will see a pop-up window that looks like this. In the left-hand box will be a list of all of the variables that we have in our file. Now, in this file, we only have one variable, which is each man's height according to their dating profile. So we would select that variable from the list on the left and click the arrow box in the middle to move that variable to the test variables box on the right. Now, this is the most important part of running this test. On your screen, if you're following along, you will notice that underneath of the test variables box, there is another little box called test value. That is where we have to input the value of mu. In other words, we have to tell SPSS what number we want to compare our sample against. Now again, if you're following along, you will see that by default, the number in that box is going to be 0. And if you clicked OK right now, the test would run, you would get results, but they would all be wrong. And the reason for that is, in this case, mu is not 0. Mu is 175.9 centimeters. Certainly the average man is taller than 0 centimeters. That's not what we want to know. We want to know if the average man's dating profile says that he is taller than 175.9 centimeters or not. So the single most important step when running this test is to make sure that before you click OK to run the test, that whatever the value of mu is, that you put the value of mu in that box. So if it's, if it was one of those sleep studies that we talked about in class, this is where you would put in 8 hours. Or if it was the SAT example that we talked about in class, this is where you would put the population average SAT score. So since we know that the average man is actually 175.9 centimeters tall, that is the value that we are going to put in this box. Then the results of the test will tell us whether the mean of our sample is or is not different from that number. This is the first time we've run a test in SPSS. That's all we need to do. Once we click OK, what will happen is a new window will pop up with the results of the test in it. And specifically, that new window will have 2 tables. This is the first of those 2 tables, and it just gives us the descriptive statistics for our sample. So first we see the value of n. We know that n means the number of people in our sample. In other words, our sample here consisted of 73 men who have a dating profile on OkCupid. Next to that number, we have their average height. Now remember, this is their average height according to their profile. So on average, these 73 men report being 178.58 centimeters tall. Next to that, we also have the standard deviation for our sample, which in this case was 6.88 centimeters. Notice also that both of these numbers have been rounded to 2 decimal places, and we're going to keep them that way. Including when we write up our answer, we always want to round the mean and standard deviation to exactly 2 decimal places. Now, if we were doing this problem by hand, step 2 would be to calculate the standard error. And as you can see here, SPSS has done that for us. The standard error in this case would be 0.81 centimeters. So looking at these numbers together, the average height in our sample, according to these men's dating profiles, is about 178.5 centimeters. But we know for a fact that the average man in the population is actually about 176 centimeters tall, 175.9. Those are different numbers. However, keep in mind, we don't yet know if they're significantly taller. So we can't draw any conclusions until we look at the results of the test, specifically the p-value, which will tell us whether there is or is not a significant difference here. If we find that these two numbers are not significantly different, then as far as we're concerned, they are the same. There's either no difference or there's a significant difference, but there's no other option. Here is the second table of your output, and this is where we actually see the results of the t-test. Now, at the top of this table, SPSS reminds us what the value of mu was, which SPSS calls the test value. We know that that was 175.9 centimeters. If we were doing this by hand, step 3 would be to calculate our t-statistic, which SPSS has done for us right here. Step 4 would be to calculate our degrees of freedom, which SPSS has done for us right here. So in this case, our t-statistic is positive 3.32, and we have 72 degrees of freedom, which is equal to the 73 men in our sample minus 1. Lastly, if we were doing this by hand, and this is where we see a pretty dramatic difference between doing it by hand versus doing it in SPSS. If we were doing this by hand, what we would do at this point is we would look in the table for our critical values, and we would compare our t-statistic of 3.32 against the critical values to see whether or not we have found a significant difference. SPSS skips both of those steps, and instead what SPSS does is gives us the p-value outright. In this case, the p-value for this test is 0.001. And it is in the column titled SIG, which, as you can probably infer, stands for significance. So in this case, we have found a p-value of 0.001. Now remember that p-values are always going to be somewhere between 0 and 1. But what we're really interested in is whether the p-value is greater than 0.05 or less than 0.05. 0.001, which is our p-value in this case, is less than 0.05. Therefore, we are going to reject the null hypothesis. Our conclusion here is going to be that we have found a significant difference, that the average height reported on men's dating profiles is in fact different, and to be exact, larger than the average height in the general population. We know that the difference is significant because the p-value is less than 0.05. We know that men's heights in our sample are larger than mu because we could either look at the means or we could look at t, which is a positive number. Remember that when t is positive, it means that m, our sample mean, is greater than mu. So we can now skip right to step 7. We know our sample mean and standard deviation, we know the results of our t-test, and we know that we're going to reject the null hypothesis in this case and conclude that we have found a significant difference. But we have to explain that finding in the context of the question that we're trying to answer. So what we just learned from doing this is that a one-sample t-test, remember always start by naming the test that you did. A one-sample t-test found that men on OkCupid reported being significantly taller than the average man in the general population. So according to the CDC, the average man in the general population is 175.9 centimeters tall. In our sample of OkCupid users, the average man claims to be 178.58 centimeters tall. So one of two things has to be happening here. Either for some reason, only taller men are using online dating services, or the more likely explanation is that there's many people who are lying about their height, which is causing that sample mean to go up. Notice also at the end of our sentence, we have the results of our t-test. T with 72 degrees of freedom equals positive 3.32, and P equals 0.001. That is another big difference from how we did this test by hand. Remember that when we did the test by hand, we ended our sentence by saying one of two things. We either said P is less than 0.05 if we rejected HO, or we said P is greater than 0.05 if we retained HO. Part of the reason we did that is because when we do this test by hand, we never actually find out what the p-value actually is. However, since SPSS is a lot smarter and faster than us, we can say what the exact p-value is by reporting the exact number that SPSS gives you. So in this case, SPSS said P equals 0.001. That's what we're going to write in our answer. It's very different from how we're doing the test by hand, but we're getting at the same thing. One last thing to notice about this write-up. All of the numbers that we calculated, so the mean, the standard deviation, the t-statistic, all of those numbers get rounded to 2 decimal places. The only exception to that rule is the p-value. Because p is such a special and important number, p gets reported to 3 decimal places, and it is the only number that we should always report to 3 decimal places. Sure enough, here's an actual graph showing the red curve is the height distribution of men in the United States. The blue curve is the height distribution of men on OkCupid. So as I mentioned before, it looks like what's happening here is that men are largely lying a little bit about their height, trying to make themselves appear taller than they actually are. Although it's technically also possible, although very, very unlikely, that for some reason tall men are more drawn to do online dating. What about women? This whole example has focused only on men, which might make you wonder, do women also lie about their height on OkCupid? There is a second data file on our website called OkHeight2, which again includes the height of a bunch of OkCupid users, but in this case, all of those users are now women. So what we can now do with this data file is we can perform yet another one-sample t-test to see whether women, like men, also overestimate their height, or whether women are more honest, or maybe women actually underestimate their height. Maybe they actually want to appear shorter than they actually are. In order to test this hypothesis, we need to know the value of mu from the CDC. So according to the CDC, the average woman in the United States, adult woman, is 162.1 centimeters tall. So just as we did with the men, what we can do now is we have a sample of women who use OkCupid. We can compare the average self-reported height in our sample against that number, 162.1, to see how the content of women's profiles does or doesn't differ from that number. If we were to run that test, and again, we would go to Analyze, Compare Means, One Sample T-Test, and we would want to make sure that we put the appropriate test value in the test value box, you should get output that looks like this. So let's quickly run through this output again and see what we have here. First, we see that n equals 60, so our sample consists of 60 women who have dating profiles on OkCupid. Our mean for those 60 women is 163.68 centimeters. So across these 60 women, the average height according to their profile is 163.68 centimeters. Next to that, we have the standard deviation for our sample, which is 6.03 centimeters. We have our standard error, which we would normally have to calculate by hand. We have our t-statistic, which we would normally have to calculate by hand. And we have our degrees of freedom, which is just our sample size 60 minus 1. We can also double check up here to make sure that we've input the correct test value. So 162.1 centimeters, that matches what is in our null hypothesis above. Here is our most important number. This is our p-value, our sig value. And in this case, p equals 0.047. So again, we're going to look right at this number and we're going to ask ourselves, is this number greater than 0.05 or is this number less than 0.05? In this case, it is, again, less than 0.05. Even though it's barely less, it's still less. So we would say, once again, we have found a significant difference here. That the average height of women on OkCupid, according to their profiles, is actually larger than the average height of women in the general population, which is 162.1 centimeters. So again, here's what our answer to a question like this would look like. A one-sample t-test indicated that the average height of women on OkCupid was significantly larger than the population average. So across the United States, the average woman is about 162 centimeters tall. But if we look at a sample of women on OkCupid, their average height, at least according to what they say it is 163.68 centimeters tall. Notice again at the end of our sentence, we report the results in APA format. T with 59 degrees of freedom equals positive 2.03. This number is positive because it appears that women are overestimating their height. And our p-value of 0.047 tells us that that is a significant difference. And notice again, we did not put a less than or greater than sign here. When we do a problem like this in SPSS, we are going to report the exact p-value to 3 decimal places, whereas every other number only gets 2 decimal places. Sure enough, here are the real data. So the light red curve shows the actual distribution of women's height in the general population, and the pink curve shows the distribution of heights of OkCupid users. It looks like, surprisingly, not only do men lie about their height to make themselves seem taller than they are, women also lie about their height to make themselves seem taller than they are. Here's our next example based on an article that came out a few years ago in the Baltimore Sun. Notice the headline, Maryland students score above national average in newly released SAT scores. Now, was this a significant difference? That's what we're going to try to find out. According to the output on the screen, the first place we're going to look here is the test value. What the article says is that across the United States, the average SAT score on the math section of the SATs was 517. So that is going to be our mu value here. 517 is the national average. In our sample, we have 208 high school students from Maryland who took the math SAT, and their average score was 518.22 with a standard deviation of 69.47. The t-statistic comparing the mean for our sample against mu, t comes out to 0.25 with 207 degrees of freedom. If you look at the p-value here, you see that the p-value is very large. It is 0.80. 0.80 is much larger than 0.05. Therefore, we would retain the null hypothesis in this case, and our conclusion would be that we have not found a statistically significant difference. In other words, we have not found strong evidence of a difference, so our conclusion is going to be that Maryland students are actually no different than everyone else. This reiterates one of the points that I've made a few times now. Even if our sample mean isn't exactly equal to mu, all we care about is whether it was a significant difference or not. So in this case, the national average on the math SATs was 517. In our sample of 208 Maryland students, they actually did a little bit better than that, 518.22. So mu and m are not equal to each other in the sense that they're the same number. However, the results of the t-test, namely the fact that the p-value is so large, tells us that the difference between those numbers is not statistically significant, and therefore we shouldn't care about it. In other words, the test is telling us this difference could just be a fluke, and we don't have strong evidence to believe that Maryland high school students really are better than the national average. In fact, first here's how we'd write up our answer. Always start by naming the test that you did. So a one sample t-test showed that the average math SAT score of Maryland students was not different from the national average. In blue, I've inserted the appropriate descriptive statistics. So the mean for Maryland students was 518.22. Here's the standard deviation for Maryland students as well. And then next to where it says national average, I've provided the value of mu so that the reader knows what the national average was. Our t-statistic here was very small, right? Remember that when your t-statistic is very small, meaning close to 0, your p-value is likely to be very large, and vice versa. As t goes up, p goes down. So in this case, we did not find a significant difference. Our conclusion is going to be we don't have good evidence to believe that Maryland students are really different from anybody else. And in fact, if we go back to the article and we read the fine print, we actually read what the article says. It says Maryland public school students averaged 528 in the language section, 518 in math. Both of these scores were 1 point higher than the national average. So while the headline might lead you to believe that Maryland students were doing way better than everybody else on the SATs, when you read the fine print, you see it was only a 1 point difference, which, as you know, on the SATs, 1 point is like nothing. So this is not a significant difference according to our analysis. Here is our last example, and I encourage you to pause before looking at the answer if you would like to try this on your own. This is an example that we will use our class survey data for. Each of you answered, as part of that survey, a question that asked, how many hours did you sleep last night? So we have here a sample of 75 students, namely all of you, and what we're going to do is we're going to calculate a sample mean for the 75 people in this class, and we're going to compare that mean against the recommended amount of sleep, which is, as I yawn, which is 8 hours. I must have said the word sleep too many times. We want to know if the average student in this class is getting 8 hours of sleep, significantly more than 8 hours of sleep, or significantly less than 8 hours of sleep. And since we're comparing the mean of our sample, or our class, against this number, 8, we are going to use a one sample t-test to make that comparison. If you would like, and I would very much encourage you to do this, pause the video now, open up the data file from class, and practice running, interpreting, and writing up the results of a one sample t-test. On the next slide, I'm going to show you the answer, which you can then check against your own work. Okay, so here is the answer using our class data. The average student in our class slept for 7.24 hours with a standard deviation of 1.51 hours. The results of our t-test tell us that the students in this class got significantly less sleep than 8 hours. We know it's significant because the p-value that SPSS gave us was very, very small, and I'm going to talk about this in just a second. We know it was significantly less, not significantly more, because the t-value is negative here. The t-statistic was negative 4.35, which is telling us that the difference between the students in our class and the test value of 8 was the equivalent of negative 4.35 standard errors, which we talked about in class on Monday. Now, one thing is a little bit different about this write-up compared to all of the ones that we've seen so far. A few minutes ago, I mentioned that if you're doing a problem by hand, you're going to write one of two things at the end of the sentence. You're either going to write P is less than 0.05 if you rejected the null hypothesis, or you're going to write P is greater than 0.05 if you retained the null hypothesis. But if you're doing a question like this in SPSS, you're instead just going to write P equals and then put whatever number SPSS gives you. So if SPSS says P equals 0.234, you're going to write in your answer P equals 0.234, not less than, not greater than. There is, however, one exception to that rule. Sometimes you will run a test in SPSS and you will look at the p-value and you'll see P equals 0.000. That's what would happen if you did this question in SPSS. Now, as we talked about last week when we talked about p-values for the first time, P can never be 0. In other words, we can never be 100% sure that we made the right decision. Maybe we were that 1 in a billion people who just by dumb luck happened to draw 10 red cards in a row from a normal deck of cards. It's incredibly unlikely, but it's possible. In other words, the probability of it happening is not 0. P can never be 0. When you see SPSS give you a p-value of 0.000, what's actually happening is the p-value is so small that it rounds to 3 zeros. And if you're curious about this, you can actually double-click on the p-value in SPSS, and it will show you more decimal places. So if you see 0.000 on the screen and you double-click on it, what you might then see is that the actual p-value is something like 0.000004. But since it only shows us the first 3 decimal places, all we see is zeros. So we need to be smart enough to realize that P can never be 0. And we should never, ever, ever write in our answer P equals 0. So most of the time when we do a problem in SPSS, we are going to write P equals blank, whatever it gives us. The only exception to that rule is if SPSS gives us 3 zeros, we are going to write what's on the screen right now. We are not going to write P equals 0.000 because that's not possible. Instead, we would write P is less than 0.001. This is our way of saying that P is an extremely small number in this case, while still acknowledging that P can't be 0. Before we move on, I want to again reiterate, make sure your answers to questions like this are complete, grammatically correct sentences. In other words, I should be able to remove the numbers from the sentence, and the sentence itself should still make sense. A one-sample t-test showed that students in our class got significantly less than the recommended amount of sleep. That is a complete, grammatically correct sentence that even a non-statistician should be able to largely understand. So that will be our goal, and that's what we will work on throughout the rest of the semester. In fact, all of the problems that we do from here on out, including the problems that will be on the final exam, will require an answer that looks like the ones that you see on the screen. So there will be a lot of practice with SPSS and a lot of practice with writing up our results in a way that's easy to understand.